I'm going to talk about a problem I've been thinking about for decades, but we made a little bit of progress a year ago when I was visiting Rome and Barcelona. And this is joint work with Ciliberto from the University of Rome too, and Joaquim Roy from the University of Autónoma in Barcelona. Just try to set up. I'm going to talk about sort of the basics of the problem, and then three sort of famous conjectures about the problem, and then tack a little bit away from the focus on a single problem of degrees and multiplicities to the entire space of degrees and multiplicities, where the problem then can be recast. Some aspects of the problem can be recast in terms of the whole subset of systems which have certain properties. And that leads to more conjectures, and finally, maybe there's a theorem. So the general setup is take the plane, take C2, and work over the complexes, and take a bunch of points, say n general points in the plane. They should be general, you'll see why in a moment. And some integers, one integer for each point. And then you consider a polynomial in the two variables. Fix the degree, so you have another parameter, the degree. And what does it mean for a polynomial to have multiplicity m at a point P? It means that f and all the partial derivatives vanish at the point P up to order m minus 1. So multiplicity 1 means that it vanishes at the point, the polynomial itself. Multiplicity 2 means it vanishes at the point and both first derivatives vanish at the point. If you center the point, if the point is the origin, you change coordinates such that the point is the origin, what it means to have multiplicity m means that when you write the polynomial out, it starts with monomials of degree m and higher. There's no monomials of degree less than m. And so you can ask the question, what's the dimension of that space of polynomials? So you fix the degree d, and you ask that they start with monomials of degree mi at each when you center coordinates at each pi. Okay. What's the dimension of that space of polynomials? You can ask this in any dimension. If you ask it in dimension 1, it's trivial, because because in dimension 1, to have multiplicity m means that at a point P means x minus P factors out. So you just drop the degree and whatever's left, that's the space of polynomial. So in dimension 1, it's trivial. In dimension 2, this question is not known. Okay, it's not known in any dimension at this level of generality. Now, of course, you have to have general points, because if I put all the points on a line, for example, and you ask for sort of small degree, the line will factor off and you get weird answers. So you generally make this assumption of general points. So it's not known in general. It's known for small numbers of points. And a relatively complete answer is known for 9 or fewer points. Okay. And it's known for low degree. Just by bare hands. We know everything about conics and cubics and most things about quartics and quintics. But even asking the question, okay, maybe you don't know the dimension of the space at this generality, but is there a polynomial at all? I mean, is the space positive dimensional? That's not known either.
That's horrifying.
What?
That's horrifying.
It's very embarrassing. Okay, well, usually instead of working in C2, you can ask all these questions in the projective setting, of course, and then you talk about homogeneous polynomials, but it's equivalent. Since the points are general, you stay away from the line of infinity. You can make the statements about C2 or P2. All right, so what do you get from just naive dimension counts? So if you have a degree d polynomial, it has this many monomials. That's how many coefficients you've got. And if you want to impose multiplicity m, this many coefficients have to be 0. And that's asking all the it's that many linear conditions. Now, if you have more monomials, I multiply by 2 here, so you divide by 2. If you have more monomials than you have conditions, well, then there's going to be a solution. Right? You're imposing a bunch of linear equations to a big vector space. If you impose fewer conditions than the dimension of the vector space, you will have a kernel to the. So you will have a non-zero polynomial. So that's a naive dimension count. All right, so let's think about organizing the information a little bit more. Fix the number of points n, and that means you have n plus 1 integer parameters. You have the degree d that you're asking about, and a multiplicity for each point. So you can consider this n plus 1 tuple of integers as sort of defining the problem for you. Okay. Now you might say, well, doesn't the answer change depending on where the points are? And the answer is not if they're general points. You get the same answer if the points are general. If you put the points in special position, the dimension could go up. But for general values of the points, you get the same answers. So it's really the integer parameters that matter, not the positions of the points for this problem. And the Picard group, if you take the plane and you blow up the endpoints, the Picard group has one parameter for the degree of the polynomials and a parameter for each of the blown up points, namely the multiplicity space. So the Picard group is generated by the line class and the exceptional divisors over the points. So there's also n plus 1 parameters in the Picard group. So this is essentially equivalent information to giving an element of the Picard group. And you can tensor with Q and consider not just integer values, but rational values. That doesn't make sense for asking the polynomial and multiplicity questions, but bear with me. You can tensor with the rationals and look at the rational vector space. And maybe that's of some use because the integer setting can be annoying from the point of view of the number theory of it all. Excuse me, you too. Sorry. And then you can also tensor with the real to get a real vector space and look at real cones and things like that. And of course, these you can think of them as embedded in each other. The integer parts are a subset of lattice inside the rational parts, which is the dense in the real vector space. All right. So now let me remind you of the intersection theory on this situation. So Bezout's theorem says if you look in the plane, now we're in the projective setting, you look in the plane, two curves of degree d and e intersect in d times e points. Okay. Now, if you have curves that meet with multiplicities, so suppose I have a curve with multiplicity 3, so there's what a multiplicity 3 thing looks like, 3 branches when including and what if it meets a curve with multiplicity 2 at the point? Well, how much should this count? This counts 3 times 2, the product of the multiplicities, because every branch meets every branch, so contributes 1. And so if you define this quadratic form, it's sort of counting the intersections that are not implied by the multiplicity conditions, right? The rest of the intersections. So this is all of the intersections. I take away the ones that come from the points, from the multiple points. Take those away, and what's left, the difference, should be the extra intersections. How many times does the curve meet outside of the end points, these two curves? The rest of the intersections. It's a very valuable tool for the intersection theory. You can, if you have a curve C with parameters d and mi, you can look at its self-intersection, which is the squares there. the canonical class of the projective plane blown up has these parameters. It's the anti-canonical is degree 3, and it passes once through each of the points. And then if you intersect a curve D and MI with the canonical class, or the anti-canonical class, you get this quantity, 3 times D minus the sum of the MI's, because the 1 times MI is MI, so that's just this. And if you look at this equation and this equation, you see that the naive dimension count that I wrote on the previous is exactly this. C squared minus CK. If you look, for example, at the degree part, it's D squared plus 3D. That's exactly the quadratic and the linear term of the naive dimension count. D squared plus 3D. Believe me, it all works out that this condition is the naive dimension count. You sort of coalesce the constants. It takes into account the quadratic multiplicities. And all this means is that there are more monomials available than you have conditions, linear conditions. And a curve should exist. Okay. Now this is always an even number, so that factors in occasionally. Any questions about that?
Why is that an even number?
It's basically because these are even numbers. Because this is the product of 2 consecutive numbers here, and one of them is even. All right. So it can happen that there are sort of special curves that sort of appear, that sort of drive a lot of the geometry of this. We say that an irreducible curve is a -1 curve if the square and the intersection with the canonical is both -1. Okay. Example would be a line through 2 points. Okay, so if you just take the parameters d equals 1, and then you have 2 points, each of multiplicity 1. So you take 2 points, and then you ask how many curves of degree 1 pass through both of those points. Well, there's only one. Now, what's the self-intersection? The self-intersection is d squared minus 1 squared minus 1 squared. That's -1. And the canonical, remember, is -3, 1, 1. And the intersection of this with this is a -3 plus 1 plus 1 gives a -1 also. So this is a -1 curve. Another example, you take a conic through 5 points. 1, 2, 3, 4, 5. So here d equals 2, and you ask it to pass through 5 points. And then you see the self-intersection is 4 minus 1 minus 1 minus 1 minus 1, and also the intersection of the canonical is -1 too. And numerically, if you look at that naive dimension count, you calculate this, you get 0. 0 is bigger than that -2, which was our naive. Then it certainly will exist if you have parameters. Okay, so these things exist. But if you look at twice the curve, okay, look at the parameters you get by taking twice the curve. So for instance, what's twice this? Twice this would be a conic that has got 2 double points. Okay. It turns out that should not exist, right? If you take c squared, you get -4. You take c cubed equals -2. This number is exactly the boundary condition. It's equal to -2, and the condition was it should be bigger than -2, strictly bigger than -2 in order to guarantee a solution. So this one misses. It's not guaranteed solution, but there is one, right? And what is it? It's the double. It's the line through 2 points. You take that polynomial and you square it. It has multiplicity 2 everywhere, in particular at the 2 points. So it should not exist because this failed, but it does. Okay. All right. So we're starting to see there's some kind of numerical subtleties in the situation. All right. So let me expose a little bit what this the difference between the virtual and the expected dimension. So.
Oh, sorry, can I ask a quick question?
Yeah.
So that dimension count you had that had to be greater than -2, was that for the naive dimension of polynomials to be positive or just to be 0?
The dimension of the space would be positive, so that there would exist a polynomial, exist a non-trivial polynomial. Of course, the 0 polynomial always satisfies all the conditions. So you have a kernel of the problem always has a 0 solution. The question is, do you have any other non-zero solutions, non-zero polynomials to the problem?
So here, I mean, there's a single curve, but there's a positive dimensional space of polynomials.
There's a one-dimensional space, namely that
Yeah.
the square of the line
Yeah.
and any multiple.
Okay.
It's a constant multiple. All right, so suppose you have a class like this. You have the vector space of polynomials that satisfy the conditions. Polynomials of degree d with multiplicities at least mi at the points pi. What's the dimension? Well, you have what we call the virtual dimension, right? You just take all of the number of coefficients you have and you subtract off the number of conditions. And it turns out you can write that in terms of the intersection form, as I explained earlier. And it's this number plus 1, which is why that -2 gets into play when you ask this to be strictly positive. The expected dimension, though, this number can be quite negative, of course, if you ask for lots of multiple points, right? And you have very small degree. So it's silly to call this an answer. You should take the maximum. If this is negative, just the expected is 0, right? 0. So that's the expected dimension. The virtual dimension and the expected dimension. And the naive conjecture would be that the actual dimension is the expected dimension. And that's false, as this -1, the double of the -1 curve illustrates. This, the actual dimension of this is 1, namely all the multiples of the double line. But the expected dimension is 0. Too bad. Okay? So the naive conjecture, I won't even call that one of the 3 conjectures. It's sort of almost immediately false with just, a line and the point. All right, so this is Segre's conjecture. So I'm going to talk about some of the main conjectures in this space. Segre's conjecture, this is Benjamin Segre. He made this conjecture in the 30s, I think. If there is an irreducible polynomial that satisfies the conditions, then the dimension is the expected. This,
You ruled out all the obvious kind, for example.
yeah. So this is not an irreducible polynomial. It's the square of a line, so it's clearly not an irreducible polynomial. And it turns out all of the counterexamples known to Segre had sort of multiple components. This conjecture is not known for 10 or more points. Very embarrassing. So refinement was developed in the 80s. It's called the Segre-Gimigliano-Harbourne-Hirschowitz conjecture. And it says, look, suppose the dimension is bigger than the expected. Okay? So you have the wrong answer. There are more polynomials than there should be. Then there's a -1 curve, which sort of splits off at least twice. This is the equation of the -1 curve will factor out of the polynomial, every polynomial, twice at least. That's what this condition implies, which was what happens here. So if g is the equation of that -1 curve, g squared factors out of everything. This is a very, very much more precise conjecture than the Segre conjecture. And this is not known for 10 or more points.
Does this imply the Segre?
Yes. They're closely related. This is a little stronger than the Segre's conjecture. both Segre and SGHH are known for nine or fewer points. You don't have so many points. It works, and basically the reason why is because the canonical class is effective. So you have a cubic, leave points. You can play games with the cubic. So you restrict to the cubic, or you can put all the points on the cubic. And just do curve theory instead of surface theory. All right, now finally, I want to talk about Nagata's conjecture. Nagata's conjectures, he was trying to prove, or actually disprove, Hilbert's 14th problem. Hilbert's 14th problem said that it asked the question, is a certain ring of invariance finitely generated? What does that got to do with this type of problem? Don't get me started. It's a whole 2 more hours of lecture. But, along the way, Nagata constructed a counterexample. And he found a group action on a vector space for which the ring of invariance was not finitely generated, and he found it using group actions on spaces associated to these Picard groups of these kinds of surfaces. And his conjecture was that for 10 or more points, if you have this condition, square root of n times the degree is smaller than the sum of the multiplicities, then there is no curve. The degree is too small. Right? And in fact, there's a refinement within this 9 that you need strict inequality. And he proved this for all perfect squares 9 or more. Okay? 9, 16 is the next one. It's true for n equals 16, 25, etc. And it's not known for any n bigger than 10, again, unless it's a perfect square. So it's again, pretty embarrassing.
Is there a special thing for 10?
Yeah, I mean, that's the boundary of when the canonical class is effective. It's exactly when the canonical class, or the anti-canonical class, ceases to be effective. Because the anti-canonical class is cubics through the points. And if you have 9 or less general points, you can find a cubic through the 9 points, but you can't make it go through the 10th general. Because there are only 10 monomials for cubics. All right, so now let's shift our attention to the sort of Mori perspective of the rays and cones in the Picard group. So let's look at this real Picard group, the real coefficient. So it's a real vector space. A ray is just all the non-negative multiples of a vector. So it's sort of half line. And a rational ray is the non-negative multiples of a rational vector. Okay, that kind of, and every time if you have a rational vector, submultiple is an integer vector. You clear the denominator, so it's all non-negative multiples of an integer vector. And so you have, you can look at the Nagata ray, which is square root of n and all ones. And the reason why this is interesting is because intersecting with the Nagata ray is exactly Nagata's conjecture. Because this exactly is a condition that the intersection with the Nagata ray is less than or equal to 0. Right? The Nagata ray is the square root of n, and in all ones, right? And if you have d's and some of the n's, right? When I intersect these two, I get d times the square root of n minus n1 minus n2. And so this condition, the hypothesis of Nagata's conjecture exactly says the intersection with the Nagata ray is negative. So that's apparently an important ray to look at, or an important vector to look at. And that's sort of why you need to leave it's convenient to leave the domain of just integer things when we start analyzing things. The anti-canonical ray is this. -1 rays are rays generated by -1 curves, where the square is -1 and the intersection of canonical is -1. Now, if you have a ray, okay, then the degree doesn't make sense, right? Because it's all multiples. But the sign of the degree makes sense because it's all positive multiples. So if you have any positive multiple where you start, this quantity here is positive, you have a positive multiple of this will have a positive number here still. So the sign of the degree being positive or not makes sense. And the square makes sense because again, if you take this and square it, if you multiply that by a positive number, the self-intersection gets multiplied by that positive number squared, which is always positive. So its sign doesn't change either. So these quantities don't make sense for rays, but the sign makes sense, which is a useful remark. Okay, so now we're going to look at a class. We're going to say the class is effective if there's a polynomial. Okay? An effective class means we have a polynomial. And a rational class is effective. What does that mean? It means some integer multiple has a polynomial. Okay? There's some polynomial somewhere along that ray. Some multiple has a polynomial. And so a rational ray is effective. We say a rational class is effective if some multiple is effective. And a rational ray is effective if there's an effective ray. There's a polynomial somewhere along the ray. And it's easy to see the sum of two effective classes is effective. Because if you have a polynomial here and also a polynomial here, the sum is use the product of the two polynomials. And what Riemann-Roch says is if you have a rational ray, the degree and the self-intersection are strictly positive, then eventually some multiple will have a polynomial in it. Okay? Some multiple. And all that means is as you increase the numbers large enough, you'll have more coefficients than you have multiplicity conditions. That's all. The naive conjecture kicks in. And that's just a fancy way of saying that is Riemann-Roch kicks in. All right, now, in this vector space, then you have the opportunity to ask any questions about rays. Is there a polynomial along somewhere in this ray, etc.? And so we call that the effective cone, EFF. It's the cone generated by the effective rays. Okay? And it's a cone because of the remark about the sum of two rays. That's the cone we really want to understand, right? And then I want to know, okay, maybe for low degree, if the degree is low, but eventually there's a polynomial. Okay? So I'm shifting my perspective. Let's not look at just one degree in multiplicity, but in all the multiples of that, and see, can we find a polynomial? The Mori cone is the closure of that. So this effective cone might not be closed. Okay, it could be the case that as I get to the boundary of the effective cone, get closer and closer to the boundary. At the boundary, the polynomials are no longer available. So that could happen. So the closure of that effective cone is called the Mori cone. This was introduced by Mori back in the 80s in his famous set of papers on issues. Okay, then you have what's called the Nef divisor. So the Nef divisors are numerically eventually free, is what the acronym is supposed to be. It means that it meets all of the effective divisors non-negatively. Okay. Something that moves will meet any effective divisor non-negatively. Moves, right? And that's the theory. And so the Nef cone is also a cone. It's the cone of the Nef classes, and it turns out it's the dual of the Mori cone. The Mori cone is the closure of the effective ones. The Nef things are the things that meet the effective ones non-negatively, and so they're dual to each other. So the Nef cone and the Mori cone are dual with respect to the intersection form. And they're both closed, okay? But the effective cone may not be. Then you have the non-negative cone. So that's the cone of classes, as I said before. This makes sense, where the degree is non-negative and the self-intersection is non-negative. So that's the non-negative cone. those are sort of the easy ones to understand. And then you have the ample cone, the interior of the Nef cone. That's where this number is strictly bigger, okay? Strictly bigger. So it actually meets every curve. It doesn't miss any curve. That's called the ample cone, and that's the Klein criteria for ampleness when it meets all the curves, positive, strictly positive. It's the interior. So you have all these interesting cones. All right. So what does Mori's cone theorem say about the situation? So you look at all the curves that meet the canonical non-negatively, and call that K super non-negative and K super non-positive dually. And you define the Mori non-negative part to be things in the Mori cone, closure of the effective cone, which meet the canonical non-negatively. And similarly, the Mori non-positive part. And clearly, as cones, Mori non-negative plus Mori non-positive adds up to Mori. Okay, everything is, take the Mori cone, and half of it would be on the non-negative part, and half of it's on the positive part. Okay, whatever. Now, if you have a -1 curve, that is in Mori non-positive. Okay? Because the -1 curves meet the canonical class in -1. Right? See, E dot K is -1. So, but it's effective, right? It's a -1. It is a curve, so it's effective. So it's in the closure of the effective cone. It is in the effective cone. So it's in Mori, and it's in Mori non-positive. Okay, so Mori's cone theorem says the following: the Mori cone consists of, is a sum of, in the cone sense, of the Mori non-negative stuff plus -1 curve. Okay, so think of it this way: you have this cone, so it's some kind of cone in this high-dimensional space, and this is where K equals 0. This is the hyperplane with intersection K equals 0. This is where K is positive, and this is where K is negative. Okay? The intersection with K is positive, so dot with K equals 0, dot with K is negative. What this is saying is, you have whatever the mysterious part of the Mori cone is here. Here's Mori, the effective closure of the effective stuff that meets positively. And on this side, you have the individual -1 curves. -1 curves. Okay? That's the cone theorem. It says that the Mori cone is composed of an unknown structure over here, but the structure over here is almost polyhedral. It's generated by these -1 curves. And moreover, the -1 curves there's not a finite number of them, but they can only accumulate on the boundary. So you can have an infinite number of them, but the complexity is all happening on the boundary of the K equals 0. So if you stay a little, if you fix an epsilon and ask, I want the dot with K to be bigger than epsilon instead of bigger than 0, bigger than minus epsilon, you stay a little bit away from 0, it's a finite number. Okay? That's the Mori cone.
So in this picture, the cone's like coming out of the board.
Yeah, the cone is, and the vertex is behind it. It's coming
Yeah.
out.
Okay. Cool.
I'm taking a slice of the
Right.
Mori cone. Fancy. All right. So if you have 8 or fewer points, and the anti-canonical class is ample, the effective cone is inside K negative. So Mori, the closure is inside K less than or equal to 0. It's all over here. And so Mori's theorem says this part is empty. And in this case, which is the case of Del Pezzo surfaces, the effective cone is generated by -1 curves. So that's sort of a famous statement that the 19th century geometers sort of struggled with all of, they wrote thousands of papers on this thing. And Mori came and said, so proved the cone theorem, and so it really was a big advance. If n equals 9, then there are infinitely many -1 curves, but they accumulate the boundary, and there's still nothing on there. So. Well, there's -k, that's all. All right, now let's look at the Nagata ray. Okay, let's assume n is bigger than or equal to 10. We have the Nagata ray. Remember, a divisor is Nef if it meets all the curves non-negatively. Okay, and so Nagata's conjecture, what did it say? If this quantity, square root of n times d minus the sum of the mi's is bigger than or equal to 0, as long as n is bigger than 10. If it's effective, then this has to be bigger than or equal to 0, because Nagata's conjecture was the converse. If it's less than or equal to 0, there's no curve. Okay? So if there is a curve, this quantity has to be non-negative. And this exactly says that this ray, this square root of n ray here, is Nef. Right? It says anytime I have an effective thing, this thing is non-negative. Right? So it exactly says that this ray meets all of the effective curves non-negative. So Nagata's conjecture basically says that this irrational ray is Nef. This is one of the power of passing to the real setting instead of sticking with the integer setting, because you get a very interesting sort of result here, but you have to kind of work with irrational vectors. This Nagata ray, by the way, its self-intersection is 0, right? Because there are n points here. Right? And so if I take d squared, I get n minus 1 for every point, minus n, it's 0. So you're right at the boundary of the self-intersection of this positive cone. Right? The positive cone was the stuff that had positive degree and positive self-intersection. This is 0 self-intersection, so you're right at the boundary. Intersection with k is positive, strictly positive. All right. So we've been talking about these cones. You have the effective cone of curves. You have the Mori cone, which is the closure. You have the Nef cone, which is the dual. You have the non-negative cone, which is the. And all of them you can apply positives and negatives to, depending on how they intersect with the canonical. All right, so there's a lot of structure here. There's a lot of cones running around. Yep. Cones are, of course, unions of rays, because you have vector in the cone and the whole rays in the cone. And so you could try to understand the cone by what's called the extremal point, sort of the boundary of the cone. And the boundary kind of determines the cone, because it's a cone. And so we say that a ray is extremal if it's not the sum of two other rays on the cone. And if you have a polyhedral cone, so think of this as a slice, and the origin is behind the board, it's coming out. You slice, you get this. The extremal rays are the vertices, because things in the it's not just the boundary. You really have to go to the super boundary, right? Because if you're in the interior of a line segment, this is the sum of two others. So it's really these corner things which are kind of focus in on with the definition of extremal. And if you know the extremal things, then those give you the cone too, right? So if you know the boundary, you get the cone, but you really only need to know the extremal rays, and you get it. Okay, this is not too hard to prove, but it does use some machinery. I'm not going to prove it. To probe the boundaries of these cones, okay? Suppose you have a ray. It's rational ray, square 0, and it's not effective, so there's no curve, okay? Then, it's Nef. It meets all the curves non-negatively, and it's on the boundary of the effective cone, and therefore also the Mori cone. And it's extremal, Okay, you can't write it as the sum of two other ones. And it meets the canonical non-negative. Meets the canonical non-negative. Like I say, I won't. This is rather technical. It involves there's a risky decomposition argument. I'm not prepared to do that. So it's going to take 20 minutes to go through it, but it's a very useful thing because it allows you to. If you can find such things, you immediately get a lot of information about a Mori and F cone because you get these extremal rays in the cone. All right, so now remember, what do you need? You need rational square zero, but not effective, no curve. Okay. All right, so if it's rational, not effective, square zero, we're going to call that a good ray. Okay. Those are the ones we're after, right? It gives good information about the Mori cone and the effective cone. So, because if it's good, it's extremal, and we can, throw it into our understanding of what this effective cone is all about. But it's difficult to prove that a ray is good. Okay? Because what do you got to prove? You got to prove that. So in every ray, there's a primitive integral vector. So the smallest vector in the ray, if it's a rational ray, it's the smallest vector that has all integer things. You got to prove that this plus all multiples, there are no curves. All right, so it's not easy to prove there are no curves. There are no polynomials. It's easier to find a polynomial. Say, here's a polynomial. To prove there aren't any, it can be complicated. So it's not that easy to prove that you have a good ray. That's why the problem's hard and interesting. Now, a wonderful ray, okay, good is, we chose that word because it's not wonderful. Because it's only so good. Right? A wonderful ray would be, okay, square zero, Nef, and irrational. So these are, a wonderful ray should be an irrational limit of good rays. An irrational limit of good rays. They're also extremal, because all the good rays are extremal. So a limit of extremal things is not hard to see. These are extremal. And so wonderful rays would be an evidence for the fact that the Mori cone is not polyhedral. Right? Because if you have a wonderful ray, an irrational thing, it would have to be the limit of these extremal things. And in a polyhedral thing, the extremal rays are finite and separated from each other, so they don't have limits. So the existence of a wonderful ray would be evidence that the Mori cone and the effective cone have a curved nature to them.
Is it literally true that wonderful rays are automatically irrational limit of good rays, or just that's how you would imagine?
No, that's a lemma you can prove.
Okay, sorry.
Okay, so this would be, okay, finding good rays gives us information about it. Finding wonderful rays would give, really kind of start to round out our understanding of the non-polyhedral nature, not just to find some information about that cone, but to really, start to understand, well, this cone has got some curvature to it. It's not even locally polyhedral here, a wonderful ray. So, our conjecture, this is with my co-authors in Harbourne, we made this about 6-7 years ago, is that the Mori cone consists of the positive cone, part of the positive cone that meets the non-negative stuff, plus the minus one curve. So it's a kind of a refinement of this. The Mori cone, it tries to identify, well, this positive part, which was mysterious, is actually the positive cone. It's the stuff that has positive degree and positive square, or non-negative. Okay? So just conjectures that that's what's going on over on this side. So that's a conjecture. All right.
Delta conjecture?
This is called the delta conjecture, yeah. Or maybe this one is. So this is another conjecture that was made by conjectures. Suppose you have 11 or more. You have a rational square zero ray, which meets this Dufernix ray, which is near but not equal to the Nagata ray. It's just a little bit. Then it's not effective. Okay, but it's rational, not effective in square zero, so it's good, and therefore it's Nef. Yeah, okay, that's one conjecture. Second conjecture, suppose you have irrational square zero and meets the Dufernix ray negatively, then it's Nef, and hence wonderful. Okay. So this conjecture would be an avenue to producing good and wonderful rays, because it implies things are not effective. You don't have to prove it's not effective, which is art. And this would imply the Nagata conjecture. The Nagata, in this range of n bigger than 10, the Nagata conjecture satisfies this condition at square zero. It's irrational, so it would be Nef. And then that's Nagata's conjecture. This is not known. And by the way, any good ray or any wonderful ray would give another proof of Nagata's counterexample to Hilbert's 14th problem. So all of these are the same proof. A counterexample to finite generation of the ring of variables. Now, good rays are hard to find, but we found some about 5 years ago. And we constructed some. I mean, we actually wrote down some degrees and multiplicities and proved brute force that there was no curve in that class or in any multiple of that class. Okay. We used the degeneration method. And then a year ago, Chiro and I used the similar techniques and constructed many more families of good rays. So again, finding good rays meant we get some information. Those are extremal for the Mori cone and the Nef cone, and sort of gives us a little information about the Mori cone. But it was still unknown whether there was any wonderful rays. And no wonderful rays were known until this year this is the Theorem. So for all n greater than 10, we found wonderful rays. And they met the canonical class 0, so they're right on the boundary. This. When n is 13 or more, wonderful rays exist that are over here. Okay. And remember, we have that conjecture that this part kind of is really defined by the positive cone, the squared positive stuff. And for these special cases, 14 or more, or 13 or more, such as n minus 4 is a square, or 18 or more, n minus 2 is a square, we found wonderful rays that meet the Dufernix ray negative, which was another criteria, another interesting criteria. And so this is the first example of wonderful rays that have been constructed in the Mori cone or blow-ups of the plane. It gives some evidence that there is roundness in the Mori cone. Now, the big conjecture is, there's roundness in the Mori cone, but the Mori cone is actually this sort of square positive stuff, right? The quadratic form is bigger than equal to 0. Of course, this is round. It's a non-degenerate quadratic form. It's round. You slice it, you get conics. So, if we knew that conjecture, we would not be surprised by finding wonderful. We don't know this conjecture. This seems pretty far away from us. But at least we've got now some rays where we think it's a limit of extremal rays. There's some evidence of roundness there. And here's an example. This is the simplest example we can find. Okay? So the degree is 1428. 4 multiplicities equal to that. 7 multiplicities equal to that. And the last two multiplicities equal to that, where beta is the square root of 21. Okay? It's clearly an irrational ray. You gotta give me that. What we claim is that it is wonderful. And our proof that it's wonderful is we found a lot of good rays, which are extremal, for which this ray is the limit. You want to stare at it a little any longer? No. So what's just the outline of the proof? I'll just finish by, what do we do? So we start with a good ray. Remember, we had collected an inventory of some good rays, and we found we had good rays for all aggregating, and we start with a good ray. Okay, and now we use a Cremona transformation. Okay, so if Cremona transformations in the plane, you blow up 3 points, so you blow down the 3 lines. It changes the degrees in the 3 multiplicities. It moves your vector, your ray, to another ray. Okay, but all of the geometry stays the same. I mean, if you had a curve before, you have a curve after. If you don't have a curve before, you don't have a curve after. Okay, because the Cremona is an involution. So, okay, so you use a Cremona transformation. You transform your good ray to a second ray. And it's a matrix. You write down a matrix that does this for you. It's a 4x4 matrix because it only involves the degree in the 3 multiplicity. Okay, you start iterating that. Same Cremona over and over again. It's good for all k. Every time you take the good ray, you do a Cremona, you get a good ray. And that converges to an eigenvector for this little 4x4 matrix. The eigenvector turned out to be irrational. There's no, I mean, it's a degree 4 polynomial. The characteristic polynomial has some irrational roots, and therefore irrational eigenvectors. And this R infinity was an irrational ray, which is a limit of good rays. Now, it's always perpendicular to k, turns out. So why is that? Because you take a good ray and you intersect with the canonical. It has a fixed intersection with the canonical, but the canonical, when you do the Cremona, the degree keeps going up, and so the intersection with the canonical keeps decaying. So in the limit, you get something on the k, that intersection k equals 0 all the time, and so it converges to that. So if you want rays that are not wonderful on this line here, you want maybe something out here. It's harder. Okay, so, but not impossible. So what we did was there is a technique of degeneration where you can take 4 points and collide them together to a single point. Bring them together. Okay? Replace 4 points with 1 point at a higher multiplicity, in fact, twice the multiplicity. Now, you collide them, you produce systems which, so what you do is, what we did was we anti-collided. We took a multiplicity that was even and split it into 4. So if the multiplicity was 2m, we split it into 4 points of multiplicity n. And that's what we give a collision. Okay? So you find systems that collide to these good rays. Right? It's got 3 more points in it because you're colliding 4 to 1. So when you uncollide, you're adding 3 more points. The resulting collided system is not effective, right? The RKs are not effective. But the uncollided system can't be effective either, because if you degenerate a curve, you get a curve. So since the RKs had no curves, the TKs also have no curves. And the TKs have the character that they jump out of the k equals 0 space into the k jump right on. So what we basically found was a whole series that approached the k equals 0, and when we uncollide them, they approach something else. Right? Which is on the boundary. I should put it here. these TKs, since they just replace one even multiplicity with four of the same multiplicities, if the limit is irrational, before you collide, the limit's still irrational. I mean, it's all kind of rational operations, so you start with some rational, you end up with some rational. Okay, the last thing is, for n equal 13, we found a whole one-dimensional arc here. All wonderful rays. And not all either wonderful or good. I mean, there's some irrational rays and some rational rays on that arc. But we found a curved arc at the boundary of the Mori cone. Just a one-dimensional thing. Okay? Which is again some indication that for the statement that the Mori cone here is round and maybe it's that. This picture, here's a little picture of a curve of some degree with a point of multiplicity 1, a point of multiplicity 2, and a point of multiplicity 3. Should have shown you that before. This is sort of a picture of, what the cones might look like. Maybe a little more detail than this cartoon I'm drawing here. Here is the k equals 0 line here, okay? Here's the Dufresne line here, and here's the Nagata, intersects with the Nagata line. Point here, which is here. And the Dufresne point is over here, and the anticanonical is over here. So if you ask to intersect with these things being positive, for n equals 0 is here, because n squared is 0. The Dufresne positive is this part here, and the anticanonical positive is this part here. So this part is the anticanonical part and the anticanonical negative. This is Dufresne's negative over here. And this is Nagata, intersects the Nagata negative over here. Here's sort of a cartoon of what the cube, that quadratic part might look like. Inside here would be where q would be negative. And so here's k equals 0, so maybe this is sort of inverted from that. The minus 1 curves over here. This part is the part we're trying to understand whether it's round or not. We've got now more evidence that it's round, basically. And that's probably enough for the hour.
Questions for Rick?
So in the definition, there was at least condition for mi, right? At least mi.
A list?
Yeah, there was the multiplicity is at least mi.
Yes, well, the multiplicity of the polynomial should be bigger than or equal to mi, yeah. That means that the coefficients are 0 below a certain amount, but it could be 0 also at that amount.
Okay.
That's allowed, but it usually would not be 0 right at the moment. So if you have a triple point of a curve, it means you center your coordinates at the origin, means there's no constant term, there's no linear term, there's no quadratic term.
Okay.
Now you might have cubic terms, you might not. I mean, that's not part of the condition. So if you say multiplicity bigger than or equal to 3, that means you just don't have 0, 1, or 2 order terms. But you might or might not have order 3 terms.
So in that case, we also consider like multiplicity 4.
Multiplicity 4 curve would satisfy the multiplicity 3 condition, yes. It just happened that there are no cubic monomials, but it's not part of the condition.
But in not quite in this direction, but like the examples with the conic and the line, this is, you can find this Terracini lemma.
Yes.
And but like, is there can you do a Terracini lemma with higher osculating planes to get at?
To try and discover some roundness?
Well,
I don't know, I didn't think about that. I don't know, I'm sure. Jeff?
Okay.
Would you tolerate uninformed speculation instead of an actual question? Okay. So, I know that this, like, so if you have a tuple of real numbers, you can, like, one thing you can do is you can just declare it's rational or not, but there are also these measures of irrationality which are related to how easy or hard is it to approximate something with rational numbers.
Yeah.
And I don't know how to make sense of that on a ray, although one probably could. Anyways, that would be another source of, a way of inferring information, like if you can, because you have these things pretty explicitly, it sounds like in your case, and I wonder if these measures of irrationality would tell you something about how well, or how rapidly these
How
rational
easy it would be to approximate. So the Nagata array is the square, the irrationality is the square root of it.
Right.
So we tried really hard working with the, convergent fraction
Mhm.
approximates to
Right,
the square
yeah.
root of 10.
Yep, right,
For
right.
example,
Yeah.
because 10 is the first unknown game. So can we find, linear systems
Right.
that converge to the Nagata array
Right.
that involve the continued fraction convergence to the square root of 10? And we couldn't make that.
Okay.
We tried. Because again, our instinct was, well, that should be easier, right? If you have, it's the fastest
Yeah.
converging, things, these quadratic irrationalities. And it is the case that every wonderful array we constructed, and I gave that one example, was a quadratic irrational.
Right.
So this one involved a square root of 21. Right? The one I showed you, with all of the ones we found involved quadratic
Okay,
irrational.
okay.
So you said these are the first wonderful ray examples? Is it?
In this setting,
So are there other surfaces where it's easier to find such things?
Yeah, I think there are some tricks. I think Kato has some examples with abelian surfaces where they, using the same kind of machinery, found some irrational rays in the boundary that Mori code for some abelian surfaces. Very kind of tricky construction with products of elliptic curves and group action.